Hi, I'm Abhigya, and today I want to tell all of you a story. And the story centers around a guy that's with us today, Brian. He got a PhD in atmospheric sciences from the University of Alabama at Huntsville, and he wrote about 20 papers in about 2.5 years. As you can see, he gets stuff done. But what Brian doesn't like to tell you is the effort it takes to get that stuff done. I don't mean the effort it takes to do the research. I'm talking about all the stuff that comes before doing the research, the data collection. So imagine Brian wanted to make a classifier for, let's say, wildfires. So let's go look at how he would go about creating a data set for such a task. So he would go to Worldview and he would have to search for a wildfire. So as just looking at Worldview on my own, and now I can't see a wildfire. So I would go back to a date in which a previous date and look there. And as you can see now, I can start to see some smoke over California. This is the fire that was started by the gender reveal party in Southern California. So I found one wildfire. That's wonderful. Now I can scroll around the same day and look for more. Here's two. Okay, so I have 2 out of 300. Now I go even north. There's no wildfires in the Pacific Northwest. All right, I go east. I don't see any more wildfires east either. I can go south, the Amazon. I don't see much here either. So now I have to go to another date and start looking again, right? So we go back again and look one more time. So as you can see, data collection is a pain, right? The process I just showed you could take weeks to months to even get the data set that you desire to even start looking at a problem. And I'm sure all of you are more familiar with this issue than I am, being scientists at NASA. So the fact that scientists have to spend weeks to months to build a data set before even starting to attack the problem is a shame. It's a major block towards innovation. Not only does it impede the research process and slow it down, but it also restricts what you scientists would consider to be in the realm of possible research, because some scientists will not even attack a problem because they think it's impractical to get the data to attack such a problem. Wouldn't it be great if you were able to expand this realm of data collection and allow the creative juices to flow more freely among researchers? So that's what we envisioned. We envisioned a reverse image search engine, kind of like the one you're seeing on my screen here, where you'd give it an image of a hurricane or something else, some other phenomenon, and it would search all throughout space on Earth and all throughout time and return to all similar phenomenon. So now the scientist within seconds has a data set that they require to do their research. I've heard that this sort of search engine runs on AI. So I want to ask my friend Mike, is that what we should be doing?
Yeah, it sounds like an awesome idea to me, Abhigya. But first, let's take a quick little boot camp just to see how AI could actually help us do this. So we start with an image we'd like to search for. But our amazing state-of-the-art AI can't see images the way we do, so it can't tell one image from another. It would just get confused. So what we need is a way to represent this image with something other than just these pretty blue pixels we see here. So how do we do that? Well, this is where the concept of embeddings comes to our rescue. When we train an AI model, it's this intermediate layer here you see in the middle that provides the embeddings. They're a way of mapping data, like our images or even text or even video, into a vector representation in a meaningful way. So of course, that begs the question, what do I mean by in a meaningful way? Well, let's take a look at an example of a data set whose embeddings have actually been plotted in 3 dimensions to see what I mean visually. So this is the MNES data set, which contains tens of thousands of images of handwritten digits. Notice how similar digits are clustered closer together, like 7 and 9. Well, similar how? Well, they're visually similar. Since if you take a 7 and just put a loop at the top, you can make it look like a 9. So we see they're actually plotted closer together in this 3-dimensional space. Just like the 8s and the 3s are closer together, because a 3 looks like half of an 8. Now, the mathematician in me really wishes that half of an 8 looked like a 4, but that's probably just a Mike thing. Moving right along, we can see that the more unique looking digits, like say the 1s, for example, can be seen off to the side by themselves with just a few like skinny 7s nearby to keep them company. And what about the 2s? How do you do your 2s? Do you put a loop at the bottom of your 2, or do you keep that part flat? I'm a flat guy myself. Well, due to this variety in the way that we write our twos, you can actually see that it will cuddle up to zeros or threes or sixes, depending on the flick of your wrist. And that's what I mean by represented in a meaningful way. Similar input data will be placed closer together, and dissimilar data will be placed further apart. Some pretty powerful stuff. So we all know what a picture is worth. But in the world of AI, we say that a picture is worth 1,000, yeah, you guessed it, embeddings. So this is exactly the concept that we would like to use with the Earth images. We would like to select an image to search for. Then our AI would create the embedding for that image, and then find the distance between other image embeddings in the database, sort the results to serve up the ones with the smallest distances to our original image, in other words, its nearest neighbors. But this is all still just theory, and while I'm great at theory, well, in theory I am, Abhigya, how would we actually bring this to life?
All right, that's a great question. So before I get into that, let me first describe the three golden principles we followed to make this a reality. So first, we didn't want to make any throwaway code. We didn't want to make code that was not going to end up on a real product. So we wanted to make all our code valuable. Secondly, had to be scalable. Clearly, if you want to search all images in all of time on Earth, you have to make something that's scalable. And third, has to run beyond my laptop. Right? This can't be something that's hosted on a high schooler's machine. So let's go look at what we did. So here is, well, this just looks like Worldview, right? So let's take a quick tour. And let's say we want to get some coastline pictures, right? So we see this is the top of, I think, Libya. And the bottom is desert and the top is ocean. And so we see the coastline there. And let's get something similar to this coastline. That's our aim here. So let's see how this does. All right, so in a matter of maybe 3 seconds, I think it returns some pretty good results of similar coastlines. Okay, but let's say you want to go a step further, right? Let's try to refine this search, because I see here there's some forests in the middle. I wanted desert and ocean, so let's just click these desert ones, and hopefully, it's not guaranteed, but hopefully this model can refine our search to just desert or more desert and ocean pictures than we had before in our data set. And as you can see, the desert pictures have now moved to the top. I think these are also desert, by the way. So that's, even though there's a little bit of greenery, this is also desert. And the forest pictures have moved more to the bottom. So like this, we can, over several iterations of this, we can select the images we want and refine our search. That's one great example of the power of this search engine. Let's take another look at something that's I found very cool. Here's an island. That's not a good picture of an island. It's kind of hazy. Let's find a better picture. Let's go. There's one in the Mediterranean here. I think this is Crete. So let's take a picture of Crete and let's see what our model gives us back. We take a picture of Crete, and as you can see, there we go. So this also worked pretty well. We get pictures of islands back. So we were able to, in a matter of seconds, go through our database of about 50,000 images, search it, and get back pictures of islands almost immediately. And that's pretty impressive. So one last example. Let's go. Actually, I lied. 2 more examples. Let's go look at. Can it? We did a lot of stuff with the ocean. Let's see. Can it identify things on land as well? So let's see. Can it detect the forest? But let's not just do forest. Let's do forest with a bit of clouds. What will it do? Right. Like let's see. Can it detect the clouds on top of the forest? Right. And as you can see, we return with images of forest and clouds, not just forest. Forest and clouds, forest and clouds, forest and clouds. So this is a pretty insightful piece of technology that can be used to search very quickly a large data set of Earth images. So let's go back and see how we did on our 3 golden principles. So the first one, don't throw away work. How do we do on that? So this runs on, it's a iteration to the NASA Worldview repository. It's an additive change. We added one button that leads to a modal that displays our site that communicates with our backend. So it's a very additive change to a already deployed product. So is it throwaway code? No, it works on something that already runs in the real world. This isn't something else we made on the site. So So not throwaway code. We met that standard. Second, does it run beyond my laptop? So to look at this, we really have to look at the architecture of how this reverse search works. So let's go look at that right now. So first, when you snip an image, so this is actually the exact example I showed you, the coastline of Libya, right? So you snip an image, the image is then sent, the image URL is then sent to our Google Cloud server, right, which is a low-powered VM. In the Google Cloud server, we download this URL as its bits, and we featureize it. And it becomes a NumPy array, and we featureize it. As we featureize it, it can then be compared in our database of image features, as Mike explained, and this returns the IDs, again, as Mike explained, of the nearest neighbors to our input image, this one right here. Those IDs can then be converted into Gibbs URLs. So Gibbs is, I mean, I'm sure you're all familiar with, but just to explain, Gibbs is a API that allows you to view NASA data very quickly just by giving it, a row and column of the Earth. And basically from the IDs in our database, we can convert them into these API URLs, Gibbs URLs, and return those back to the user as the image they see on their output. So in this whole process, as you can see, none of this is hosted on my laptop because my laptop crashes, no NASA work can be affected. My laptop is not nearly important enough for that to be the case. And as you can see, this is all hosted on the cloud, and the reverse image search architecture works perfectly. But what if you wanted to have different models for different zoom levels, right? Because obviously all phenomena do not happen on the same zoom level. A thunderstorm and a wildfire happen at very different levels, right? So having the same model to try to recognize both doesn't seem correct. So we tried that. We tried to deploy models. Actually, we didn't. We tried successfully to deploy models on AWS SageMaker and CloudML, right? And it worked, and we were able to use those models as their own APIs. And the only issue was I ran out of pocket money. So we had to switch back to our low-powered Google Cloud VM, which just ran a TensorFlow model, just put on that. It works great, but this is, given funding, we would really like to revert back to this sort of scenario. This is all great, but let's look at how refinement search works, right? Because that's another cool thing that I showed you. So say we wanted to pick these 3 images because we wanted to get desert and ocean, not just a coastline. So this is on our this is on the React-based Worldview frontend, and instead of passing the image URLs back to the backend like we were doing before, what we do is we just pass the IDs back, right? Why do we do this? Because we don't want to refeatureize images, because the user could pick, I don't know, up to 30 images. So we don't want to sit there refeaturizing all of them. So you pass the IDs of the image back. Those IDs can be compared with the database that already exists, and then their features can be pulled out and compared, and then recompared with the database they were in, find the nearest neighbors, and those can be returned to the user. And as you can see, the results get refined over time. So that's the way our refinement works very quickly. But anyone listening can now realize there's a very big black box here. This fast approximate search in our database is the black box. Everything is contingent on that working quickly, right? So let's go and see how we did that. So that's our third point, has to be scalable, right? And this basically comes down to two things. First, the data has to be stored in a reasonable manner, right? If the data is stored in a manner that just is explosive in terms of size, it's not scalable. And then second, the search has to be quick. If the search is slow and we expand it to millions of images, there's no scalability at all. So let's go take a look at that. Just some background of how our database is structured and created. It's images from the NASA Gibbs API, which I talked about earlier. Basically, it's about 51.4K, and they're split over low-level zoom and high-level zoom, right? Since we don't have 2 models, they're just all in one database, and so they're about 51,000 images, right? And one thing we realized, and so we started this journey of trying to make a scalable system by just brute force searching and storing the images as images. And we ran into 2 problems very quickly. First of all, the storage was too high. Storing images as images, not practical. And second, brute force searching, extremely slow. It took something like 30 seconds to search the nearest neighbors for 5 images. So that's not scalable at all. So how do we approach this problem? So we realized 2 things. Firstly, in terms of storage, we realized that after about 100 embeddings, like a length of 100 embeddings, the accuracy that is generated by the search just tails off, right? So that means that after about 100 embeddings, doing anything after that, you're really not getting much gain. So what we were doing previously, we were using ResNet 50 as our featurizer, and that was making embeddings of about 2048, like not about, it was making embeddings of 2048 length vectors, and that was taking up a lot of storage. So what we did is we got Mike on, and Mike made this new model, and that shrunk the embedding length by 16 times, and that really shrunk our storage while keeping efficiency about the same. So this was how we managed our storage and made it very scalable. So right now, the 50,000 images are represented in our database by about 1 gigabyte of memory, which is amazing. All right, so this is how we dealt with the storage. How did we deal with search? Because obviously having the smaller length does speed up search, but that's not it. There's more. So here's some factors to consider for approximate nearest neighbor method search. So first, speed. Okay, obviously. Next, accuracy. Also, obviously, you can't sacrifice accuracy for speed. That's just shooting in the dark, right? Time to build index. So building the database and compiling it, that can't take forever, right? And the size. Again, you can't have a database that is just explosive memory. So here, this small point here on the graph of queries per second and recall, that's brute force nearest neighbor search, right? As you can see, it's a singular point on 100% accuracy because there's no other accuracy you can get with the brute force method. It's just one. It can only be perfect. So that's great. It's 100% accuracy, but it's extremely slow, 1 query per second. That's where we're getting to our issues with having a long search time for brute force. So how can we improve on this? What are the other methods that we can use? And here are the other methods. So first, we see the best method is scan by Google. There's about 5K queries per second at about a very good accuracy rate. And we would use scan. We were waiting out for some bugs in the library to be fixed. So what we used in the meantime was this green line you see here, the light green one, Annoy, which is used by Spotify. So it is an industry deployed thing. And this was our sort of middle route between this and scan. And Annoy, again, same thing. It's very fast at a very high level of accuracy. So we were able to build our data set to whatever size we wanted to, and we were able to search it very effectively and very quickly, as you saw in our demo, where the searches were just coming up in a matter of seconds. So that was really our journey from a brute force search where it was extremely slow and extremely inefficient to a very much quicker way of storage with our featurizer and a quicker way of searching with Annoy. So as you can see, the potential for the acceleration of research with this tool is immense. Currently, earth science works at a very slow pace because of the clog that is data collection. This inhibits both trained researchers, such as yourselves, and citizen scientists that just want to get their toes into science and maybe make a discovery in their free time. So with this tool, not only do we help the researchers, because we definitely do, that is our aim, we also democratize the study of the earth. We make everyone a potential ground bearer because now everyone can get the data they need to really do insightful studies about the world. This tool in that way is a catalyst I hope to see on Worldview soon. So researchers like Brian can continue to write papers faster than we can even read them. Thank you, and that's Worldview Image Search by me and Mike Levy.